Welcome to Higher Structures seminar series of Feza Gürsey Center for Physics and Mathematics. Today our speaker is Daniel Tubbenhauer from University of Sydney, and his talk is Counting in Tensor Products, and we thank Danny for agreeing to speak in our seminar series. Please.
Yeah, thank you so much for having me. It's a pleasure to come to Istanbul, just virtually, of course. And yeah, it's a pleasure to give a talk here in this higher structure seminar. My structures are pretty low dimensional in some sense, as we'll see. So I'm mostly talking about kind of monoidal categories. And this idea that is joint work with Colombier, I think of in Ostrich mostly, and some others we'll see, is that we kind of have this idea of applying methods from analysis to monoidal categories, which are usually kind of more like discrete type of objects, and want to do some various counts. So you start applying, thinking about it, developing some analytic theory of monoidal categories. And if you start trying to do that, then maybe you start with counting problems. So counting problems are always nice. If you think about it, give you some historical interlude in a second. But if you think about the standard counting problems in mathematics, very soon they get very, very complicated, and you don't count them. You don't count things anymore like precisely, but maybe you just count kind of approximately, asymptotically, something like this. And that's what I want to do. And my favorite object in this talk will be, monoidal categories. So tensor product will refer to a monoidal product with some extra structure so that my problem makes sense. And I will stay with a lot of examples, mostly coming from the realm of representations of groups. And that's what I kind of want to generalize representation of groups from a very nice kind of monoidal category. And what we'll see here is that there will be a lot of exponential growth, and I will have a lot of little diagrams of this form. So maybe let's get familiar with this. So this is what I'm showing you here is a log plot. A log plot really just means on the y-axis you put a logarithm, because if everything grows exponentially, you kind of break it down a little bit and make it a little bit more accessible. In particular, a line in the log plot is an exponential growth, right? A line in a log plot is an exponential growth. And this little picture that I stole from actually a real research paper is about the exponential growth of publications in science in general and in mathematics in particular. So exponential growth everywhere. Yeah, you can see this nice line. The black one is kind of the expected value, and then the various different Web of Science or something, and how the number of publications grows. And we will see something very similar applied to the realm of monoidal categories. So I hope you will enjoy it, and feel free to interrupt me if you have questions. Okay, but I'm trying to motivate a little bit what we are going to see, because kind of we want to copy that. So keep in mind that what I have in mind is something like an analytic theory of those categories. So I should start with some motivating examples. And the first example that comes to mind for that hopefully every mathematician will know and will like in some form is kind of counting prime numbers. So I have my little prime counting function pi, and I will ask 3 questions about pi. So pi of n is just the number of primes up to n. And I will ask 3 questions that I go through in the slides here. So kind of counting primes is like not really nice. They kind of have a lot of random behavior. So counting them precisely is a bit of a difficult task. But counting them in a different form of counting is actually not so bad. So for example, you could ask, what is actually the overall growth of this function? So roughly how many primes you should expect up to a certain bound. And it's not so difficult actually to see, so question 1 is kind of the easier one, the leading growth. It's not so difficult to see that actually roughly grows like n. So here in my plot, I have the pi function, I have the li function, I will show you the li function in a second, and I have n, and they roughly have the same behavior if you go to whatever, n equals 100,000. It's kind of the rough picture that you should keep in mind here. And people started doing this quite a while back. So Gauss always claims that Gauss has always solved everything. But the first kind of idea along the lines what I'm going to show you, kind of in a paper or in a book by Legendre. And what people were doing is they were counting prime numbers. So per formula and per table. So formula is the formula we're going to see. So Legendre was using this type of formula to count the prime numbers. And apparently the formula gives up to 10,000 gives 1,530. And the table of prime numbers, so the actual count is here on the right. And you can see that it's not so bad. So Legendre's formula here is not so bad. It's a little bit off, but it's actually not so bad. And this is this idea of counting. Whenever you can't really count, you count something different. You count it a slightly different way. So here, Legendre's approximation, n over log n, and then there was some correction factors where people were trying to play around a little bit what the correct approximation is. Legendre tried this funny factor here, 1 point whatever, and it works up to 400,000. That's where Legendre's table then ends. Okay, and that took a long time, by the way, to do. And nowadays you can just list whatever. With a computer, you can just list the first God knows how many billion of prime numbers without any trouble. But people were trying to do this count. This was really difficult, and they eventually came up with a really, really cute solution, which is called the prime number theorem. So instead of counting, you just have this idea of that the ratio gets good when kind of you have a large number, so n goes to infinity, and you have a nice function where this ratio gets good, and this is this famous prime number theorem. So the nice function approximating the pi function is n over log n. So not quite what Legendre had. So Legendre had this correction term, but n over log n is exactly what people came up with later, and this is called the prime number theorem, one of the most important theorems in all of mathematics in some sense. A little bit better if you want. So I really like this expression because it's kind of very, very simple. So the overall growth rate is this n, and then there's a sublinear correction factor 1 over log n. And this is exactly the kind of behavior that we will see as well. Historically, there's this other function which does a little bit better. It's called the logarithmic integral. Probably with this audience, it's probably not a big deal to pull it up, but I like the other function a little bit more. And I just plot them here. So the ratio gets good, really just means it should converge to 1. And you can see it here if you go to 100,000. It does a little bit bad in the beginning, but if you go up to 100,000, it kind of really nicely converges to 1. And that's the type of question I would like to ask, right? So I have some number that comes up in this study of monoidal categories, and I would like to understand it, but I can't. So I kind of try to play this game of what is the asymptotic approximation of that. Some games like this. So I'm really motivated here along the lines of this counting of prime numbers. So this is the famous prime number theorem. And then there's one more question you can ask, and that goes back to probably the most, well, let me just say the most important problem in all of mathematics, the Riemann hypothesis, which is really just a beefed up version of what I just showed you. So Riemann calculates what I will call the variance in a second, which is, I'll show you what that is in a second. And so Riemann just says, I've copied this from Riemann's paper, from 1859. And essentially, here's our logarithmic integral. Well, so the function from before. F in Riemann's notation is some version of the prime number counting function. And here you can see f is equal to the logarithmic integral. And then you have this error term down here, whatever it is, some error term. And the error term is usually called the variance. So the difference between the expected value and the real value. And Riemann calculated this and then came up with this term down here, which is fairly harmless. You should kind of ignore it. And then there's this sum, and the sum famously runs over all, as Riemann says it here, sämtliche positiven Wurzeln der Gleichung, whatever. So it runs over the non-trivial solutions of zeta equals 0, the non-trivial roots of the Riemann zeta function. And this is where actually the Riemann hypothesis comes from. So the Riemann hypothesis makes this assumption that all roots are on this critical strip, and it's related to the variance of this prime counting function in the following way. So so here's my difference. If the Riemann hypothesis is true, then this difference can be bounded like this. So n over, so square root of n times log n. And this 1/2 is exactly the how you see the usual Riemann hypothesis formulated. This 1/2 is the critical strip, in the Riemann hypothesis. And if all roots lie on this strip, then the Riemann sum can be kind of approximated, and you get this 1/2 here. Okay, so here you can see I just plotted that. It actually does really well. It eventually stays below this bound. So this is notation here. It stays below this bound. And note here kind of something fun. So I would like to ignore the logarithm. So let's ignore the logarithm. Then the variance, so the difference between the expected value, the asymptotic formula coming from the prime number theorem, and the real value grows like square root of n, while the function itself, again, ignore the logarithm, grows like n. So it's the function itself grows like n, and the error term grows like square root of n. That's some kind of behavior that we will see as well coming up in monoidal categories. So kind of the fun here will be that all of this really beautiful mathematics is kind of very classical. If you want to call the Riemann hypothesis a classical theorem, I guess everyone believes that's true anyway, will kind of be reflected in monoidal categories, which I really find is kind of really exciting and cute and nice. And this is kind of the difficulty that we will see, and I will go through it in the talk. Like starting with monoidal categories, try to answer the question of what is the leading rows in the prime example, it was n. What is the precise asymptotic formula in the prime counting example? It was this prime number theorem, so n over log n, and then the Riemann hypothesis, how good is actually our approximation, is usually a very, very difficult question, right? So to have an exercise, the prime number theorem is certainly not an exercise anymore, and the Riemann hypothesis is like impossibly difficult in terms of this prime number function. All right, so that's my motivation. I want to build a theory on monoidal categories, which kind of mimics, reflects those really beautiful and classical theorems again, if you want to call it the Riemann hypothesis as a theorem, from number theory in this case. Okay. So let's get going. So right now, I will be more precise later on, but right now, let's say gamma is anything that allows a tensor product. Think of a group if you want. And I take any ground field, and I take any new representation of my group. Any finite dimensional to make sense of the problem. And I want to decompose my tensor product into simple summons, into irreducible summons, into composable summons. Depends a bit on the problem. And the only thing I note already for you is that the tensor product itself grows exponentially, right? So the dimension of the tensor product is just the dimension of my space to the n. So in my little log plot, that's this guy here, and we'll see the others in a second. Now, so we have this problem. We want to decompose it into its constituents. That's what representation theorists like to do. You want to decompose the problem into its Lego bricks, into its Lego pieces. And yeah, I want to do that. And in this generality, like any ground field, any group, counting is probably pretty much impossible, but it turns out that you can count asymptotically kind of really nicely. I'm going to explain how that actually works out. Okay, I hope the problem is reasonably clear. I will be more precise what gamma is in a second, but what gamma could be is I really have any group in mind. And it actually is even more general what I'm going to say. You can take any semi-group. A semi-group is not a Hopf algebra because the inverse doesn't make sense for a semi-group. So semi-group is a group without inverses. But it's still you still have a what is it called? A byproduct, so you can still tensor representations. But really anything works, and if you like supergroups, you can take supergroups as well. But I'm going to ignore those guys anyway. So really very general setup. Take any group, not even finite or anything, just anything essentially. Okay. And And actually what I have in mind are way more general settings. So in order to make sense of my problem in the categorical setting, the only thing I really need is to have some additive structure, and I have a well-defined decomposition of my tensor product, right? I take a monoidal category with some additive structure, so they can have can add representations or objects, and I need to have some well-defined decomposition. And all I want is an additive Krull-Schmidt monoidal category. So additive. Krull-Schmidt is the decomposition is essentially well-defined, and monoidal is I can make sense of tensor products. And if you that's the general setting essentially that I'm going to study in a moment. For now, just stay with groups. So really anything you want, like representations of a group, very complicated categories. It turns out that you can still solve the problem. Not counting will not work. Counting asymptotically has a nice and well-defined answer, which I think is very surprising in this generality of the set, right? So any group, for example, any semi-group. Again, let me reiterate, decomposing something for an arbitrary group over an arbitrary field, that doesn't sound very doable. That's certainly not doable. That's like out of reach. But counting asymptotically will work, and that's exactly my plan B, with mimicking this idea from prime number theorem.
So I think there is one question from John in the chat box.
Chat, excellent. You're chatting as a guest. Oh no, I don't assume that it's semi-simple. No, anything. Even with infinitely many symbols. Eventually, even with infinitely many symbols. Right now, I'm as general as possible. I will be more precise as we go along. Okay, in particular, because I'm not assuming semi-simple, what I really want to see are the indecomposable summons. In this example, it doesn't make a difference because it is semi-simple, but in general, I would count indecomposable summons, and I would count them with multiplicity. So really everything that shows up. So in my example, gamma is SL2. Really just a harmless example. I take SL2. I take my ground field to be the complex numbers, and I take the defining representation of SL2. SL2 acting on a two-dimensional space, the vector representation and defining representation. And you can write down the sequence. So Bn is always a sequence, like the prime counting function, the precise sequence of numbers. And well, how does it go? Well, the zeros tensor power, a little bit boring, the trivial one. The first tensor power is just itself. The second tensor power, so c squared twice, will decompose into a symmetric and a trivial representation. So you count two summons, and then on the next step, the symmetric one will go one higher, and you will see the defining representation turning up again, and from the bottom one, you will see another copy of the defining representation. And I count, so 1 and 2 defining representations in 3. So I count with multiplicities. And then it goes on. You can easily do that with a computer, like 6, 10, 20, whatever, and so on. And I did that with a computer up to the thousands tensor power here. It's kind of a task for a computer. And okay, you get very large numbers. And the idea is now, and we'll see in a second why we want to do that. We take we expect kind of exponential growth. If you look at those numbers, they grow very fast. But maybe you could take just how do you you could take a log, but a little bit better is to take an nth root. So take the nth root of my sequence. It kind of boils down breaks down the exponential growth, and the nth root of my sequence, like here the thousandth root of my sequence. This was a bad color. Let me try a different choice. The thousandth root of my sequence goes up to 1.99265 something. So you could conjecture that it converges to 2, which really just says that the overall growth rate is 2 to the n. Right? So if I take the nth root, there will be some correction term, something like in the prime number theorem, but it's not exponential, so the nth root will squeeze it and it's gone. And whenever the outcome is 2, it really says the overall growth rate is 2 to the n. of this problem. Okay, fine. And then I tried another one. So the 3-dimensional representation of SL2. You get again a sequence 1, 1, whatever, and it grows even faster, and you can convince yourself that whatever, same type of problem, but now the 1000th root of the 1000th sequence entry is about 2.9875. So convergence is a bit slowish, but it's kind of convincing that it will go to 3, which note here is a dimension of the representation we started with. So here, this guy, dimension 2, and the convergence seems to be 2. I start with something of dimension 3, and the convergence of this nth root appears to be 3. Well, kind of problem hopefully makes some sense. I just listed the number with a machine, and I took the nth root. I had some reason to do that, and it turns out that the nth root will converge to the dimension. Or at least in this example, it looks like it will converge to the dimension. And in order to make this visible, I took a log-log plot. So here's a log on the y-axis, and there's also a log, as you can see, 1, 5, 10, 1,000. There's also a log on the x-axis. And I do this because the convergence rate is really slow. I will comment on that as we go along. So it's 1,000 standard power. It's still off by quite a bit, right? It's 2.8, 2.98. All right. Observation 1. So try to convince. I will explain the proof, by the way, in a second. But of the theorem, which I'm going to show you in a second as well. But let's just go through the observations. So my key here is I started off with representations of Lie algebras and Lie groups. Whenever something was true for SL2, it's of course true in general. And here's my setup. So a gamma could be any affine semigroup superscheme. Whatever that is, any semigroup works, for example. I can take any field, not necessarily semi-simple, but really anything. And I take any finite dimensional representation, and I want to count this number of incomposable sums. And I get an answer for all of these cases at once. Just kind of nice. Okay. The first observation you have is kind of really kind of easy classical analysis observation about sequences. So this guy will be submultiplicative. Which means this beta, which is the limit of the nth root, will always exist. So a priori, it doesn't need to exist for an arbitrary sequence, but because we have the submultiplicativity, so bn bm smaller equal than bn plus m, there's some nice lemma, or some well-known lemma that will tell you that this limit exists, right? So that's why I was taking the nth root, because I know that this limit is supposed to exist, and the real question is what is this limit? What is this beta? Yeah, the limit of the nth root. Okay, and there's the only two cases that come to mind. So beta is definitely bounded by the dimension. Why? Because the dimension of the space, the tensor product itself, only grows like dimension to the n. It's clearly bounded from above by the dimension, and it's clearly bounded from below by 1. It can't go lower than 1. And essentially, if it's 1, then you can't decompose at all. It's just one block. And if it's beta, so if it's the dimension, then everything is, all indecomposable sums are actually very tiny compared to the exponential growth. Essentially, they are one-dimensional. Like the upper bound is achieved when everything is like one-dimensional. And it should be somewhere in between. And the question is, what is it? What is it in between 1 and the dimension of my space? I will explain. Let me explain the theorem first, and then I will tell you what a superscheme is. And then, yeah, so the theorem says that beta is actually achieved at the top end of the sequence. Okay. So all indecomposable summands for any group, for any whatever, all indecomposable summands, they cannot compete with exponential growth. They're all kind of really tiny compared to the exponential growth of the space itself to the end of the tensor product to the end. Okay, so there's a question in the chat. What is a superscheme? Yeah, that's a Deligne type thing. So usually what you do is, maybe you have seen an affine scheme. So that's a semi-group scheme. A semigroup scheme would be a semigroup object in the category of affine schemes, which is the opposite of the category of commutative algebras over some field. And now what you need to do is you just take the category of commutative superalgebras over some field, and the opposite of that category and the semigroup object in that category. That would be an affine super scheme.
So I mean, monoid schemes over monoids. They said I think log schemes, right? Logarithmic schemes by Kato, as far as I know.
Say it again.
I mean, schemes defined for monoids. It is called logarithmic schemes, or by Kato, I guess.
Okay, no, I'm okay. I will definitely Google that later. I wasn't aware that there is an extra name for it.
Okay.
Logarithmic schemes. Okay.
Yeah, I think so.
Yeah. Okay, that's good. Good to know. Thank you so much. Any other questions up to this point? Okay, wonderful. Yeah. So this is the answering question 1, if you want. What is the overall growth rate? It's always kind of as maximal as it could be. It's always a little bit slowing down. Yeah, a little bit slowed down compared to the dimension itself. And let me just prove it for SO2 for you. So for SO2, so if you do the calculation and you do v to the n, where v is really just, let's say, the two-dimensional representation, right? That's a two-dimensional representation. You take the nth to the power to the n, then you can make the following count. So the minimal, the maximal dimensional representation that will show up is the symmetric power, which is n plus 1 dimensional, with n plus 1 dimensional. And if you just now say, okay, I don't know anything about the other factors that appear, but I know that this one will appear. So let's just assume everything is of that dimension, everything is maximally dimensional. Then the number of summons is still 2 to the n divided by n plus 1, right? So this is exactly this little graph here that I had before. I had it with an n instead of an n plus 1, so like this one. And you can't, basically in a log plot, you can't tell the difference of the slope of that graph compared to a dimension of the space to the n, right? And this 1 over n, which is my subexponential correction factor, that gets kind of squeezed to 1 by the nth root construction, and that's why we have the space v to the n. I'm sorry, that's why you get the beta theorem. And you can play the same game for any Lie group if you want. Well, let's say for GLN, you have Weyer's character formula. Weyer's character formula will tell you that the maximal dimensional representation has dimension of is the polynomial in the weights. So you get some polynomial correction factor, which can't compete with the exponential growth. It will die in the taking the nth root. And essentially, then you just need to observe that any other problem can be somewhere embedded into the GLN problem and can be then again bounded from below by the GLN problem, and then you're done. That's essentially the proof. So say it again. For GLN, you use a character argument. Characters, the dimensions don't grow fast enough, they just grow like polynomials, and then you essentially embed the problem into GLN.
So
Okay.
I'm sorry. So what you are saying is that GLN problem is in the end the critical part. All problems can be considered or embedded in the GLN representation problem, as far as I understand.
That's right. So just think about it like this. Say you have a group and you have a finite dimensional representation, then you can actually replace the group by its image in GLV of that representation.
Right.
Right. You just replace it by GX on V. So G, there's a map from G into GLV, and you can replace G by its image in GLV. And if you know the problem works for GLV, then you can bound it from the right side, from below, for G as well.
Can we also consider like this? I mean, G can be considered as a subgroup of the symmetric group. So considering the representations of the symmetric group, maybe
That's right. That's a different way of doing it. Yeah, exactly. You essentially what I told you works for a more general setup where you have just a symmetric monoidal category, which have a functor to vector spaces. That's all you need. You need the functor to vector spaces to make sense of dimension, and you can play the game with a symmetric group instead of GLN, and that's why you need the symmetric monoidal category. That's right. Okay. Any other questions?
I sort of got lost on why we're dividing by n+1.
Okay. The maximal dimensional representation in this space is some n of V, which is of dimension n+1.
Okay.
Okay. And now I just say, okay, I don't know about the other summons, but let's assume, I've tried to bound it from below. Let's assume everything is maximal dimensional, so everything is just n+1 dimensional. Then this is the count of the number of summons. Make sense? And this gives me a lower bound.
Is G a finite group?
Everyone happy?
Is G a finite group? Can you hear me?
No, G is not necessarily a finite group. G can be any group.
Okay, thanks.
Infinite groups don't tend to, I mean, infinite groups usually don't have many finite dimensional representations. So the only restriction is that the representation is finite dimensional. Any other questions? Okay. So this is answering the first type of question. What is the dominating growth rate? And it's kind of a nice theorem. It's always grows exponentially, right? It's always kind of the maximal thing you can imagine. So what I really have in mind is that nothing can compete with exponential growth. So essentially what the formula is showing that this Bn looks like this. There's a dominating growth rate here, dimension to the n, and some sub-exponential factor. Whatever the sub-exponential factor is. And step 2 in my program, step 1 is to identify the overall growth. Step 2 would be to identify the sub-exponential factor, which you should expect to be a little bit more difficult than, for instance, the overall growth rate is 2 to the n. Dimension v to the n. Let me show you how that goes. And it's a bit annoying, but it's hopefully not too bad. So we'll see. Okay, so I want this formula. So I want my Bn, and I call the other side, I just call it An. Right? So An is supposed to be some sub-exponential factor times my overall dimension. Okay. Now I'll show you in a second how that works. And I'll show you how general that statement actually is as we go along. But on the next slide is pretty full. I just warn you. All I'm going to say is that there's the way of solving the problem using eigenvalues and eigenvectors. So it's kind of a nice way of doing it. And I will show you a formula on the next slide. Keep in mind, all I want to say is that there's a way to find C using eigenvalues and eigenvectors of a certain type of object, which is a nice linear algebra way of solving the question. Okay, ready? Okay, way too much information on one slide. So we go through it. So what I have in mind is that I have a category. I start with a category, representations of a group. You should always keep in mind that I have some representations of a group. And really what I'm doing here is a problem of decomposing tensor product. It's really a problem of the Grothendieck group of that category. And I can reformulate it as follows. I can take an algebra, and I call it an R+ algebra, or an algebra with positive structure constants. So it has some basis, whatever. And on that basis, my structure constants are all positive. And a Grothendieck ring of a category will do the job, because the basis would be given by, let's say, the simple objects, And tensor product with simple objects will decompose into simple objects with natural numbers, right? So non-negative numbers. And I can write down an action matrix for every element. And just acting on that basis, I write down a matrix. I will give you several examples in a second. And I take the leading eigenvalue of that matrix. So the matrix, it will be some matrix, and it will have some eigenvalue, and one of them will be the biggest. Pick this biggest eigenvalue. That biggest eigenvalue is the overall growth rate. Okay? So matrix, write down the matrix, its biggest eigenvalue is the overall growth rate of my problem, the beta from before. And to get so here's my beta, right? It's now called lambda, because it's an eigenvalue. Eigenvalues are called lambda. And to get the Cn, which is all of that shit here, it's a little bit of a tricky thing, but not too bad. To get the Cn, what you do is this leading eigenvalue has a corresponding eigenvector. And it might have several depending on the multiplicity of the eigenvalue. And I call them W and V0. So it's the left one and the right one. In all problems, I'm going to show you they're symmetric, so they're the same. But in general, you have a left and a right. And you just multiply them together and just add them up according to the multiplicity, and you get a formula. Let me show you how that works in practice. Looks very, very difficult. It's actually really easy on a machine. Let me do the symmetric group for you. Finite group, symmetric group S3. Hopefully not too complicated. Field characteristic 0. I take the standard representation, two-dimensional. All right. S3 has three representations, three simple representations. The trivial representation is here, the sign representation is here, and the standard representation V is here. And this graph that you see here is the graph of tensoring with V. So if I tensor trivial with V, I go to V. If I tensor S, the sign with V, I go to V. If I tensor V with itself, so V with itself, tensor 2, decomposes S, V plus trivial plus sign, and I write this in the matrix. So here, this is the T, V, S. T times V is V, right? Again, T, V, S. T times V is V. V times itself, everything appears. V times S is V. So I write down this matrix and I get a matrix. This is what I call the action matrix. Hope it makes sense. It's how the given object acts on the set of indecomposable objects of your category. Just write that down in the matrix. And I will allow infinite matrices in a second. For now, everything is finite, just to avoid technicalities. Okay, the leading eigenvalue of this matrix will be 2, which is the dimension of our representation, which is exactly our little beta from before. The leading eigenvector will be this funny guy here. And if you just write down the problem, just V tensor W, in this case they're the same, you get this matrix and you need to take the sum of the first, oops, this was bad. You need to take the sum of the first row. 1/6 plus 1/3 plus 1/6 is, if I'm not calculating, is 2/3. And 2/3 is then the sub-exponential correction factor in this case. In this case, it's just a scalar. And the asymptotic for the decomposition problem is 2/3 times 2 to the n. Okay, let me repeat. You write down how your object acts on a given basis. You write down the matrix. The leading eigenvector of that matrix is your overall growth rate. The leading eigenvector of that matrix, if you just multiply it with itself, you get another matrix and you take the sum, and that's the sub-exponential correction factor. In this case here, I just plotted it and it converges like super quickly. Okay, because, well, the second largest eigenvector gives you the rate of convergence. The second largest eigenvector answers the problem about the variance. The largest one gives you the growth rate. The second largest gives you the variance, the discrepancy between the expected value and the real value. The second largest is 1, well, 1 in this case, or -1. So it converges really quickly because it will converge with 1/2 to the n. It will converge with this. So second largest over largest. We converge fairly fast. Yeah. So this answers in one go all questions you can ask with all my 3 questions, 1, 2, 3. This is a finite case. I answer 1, 2, 3 in one go by just looking at an eigenvalue and eigenvector problem. Let me do it one more. Let me do one more for you. So if you take, for example, the dihedral group of order 8, and I take its defining rotation representation of order 2, this is the matrix you get. This is the graph you get. Just looks, it has 4 one-dimensional representations.
Hi, Danny. Would you mind briefly reminding us where this matrix comes from?
Yes, absolutely. Let me try again here. The matrix, maybe I do it in this little smaller example. So for the symmetric group, you just write down, just list the simple representations. You have 3 simple representations: the trivial representation, the 2-dimensional representation, which I call V, and the sign representation. Okay, let me just park this somewhere here. I write down another trivial representation, vector representation, and sign representation. So I want a matrix, which is in this case 3 by 3. And the way how to get the matrix is the following. So your tensor, T tensor V, trivial tensor V is of course V. So you're right, trivial tensor V has no copy here, 1 copy here, no copy here. Sine tensor V is also V, that's a calculation you do. So this has no copy here, 1 copy here, 1 copy here. And V tensor V has everything, so it has 1 copy here, 1 copy here, 1 copy here. Is that reasonably clear?
Yes, thank you.
Thank you so much. Okay, so this is called the action matrix. So you act with your object and then decompose and write down the result in the columns of the matrix. And I just did the same here for the dihedral group. I write down the matrix is pretty small. So I write down the result. It has 5 simple representations, and the matrix will look as follows. So this matrix here, but it might be a bit smallish. I just copy it. And then a lot of zeros here. And which is really just, if you tensor the 2-dimensional representation with itself, so you have a 2-dimensional one, that's the one I choose, and you have 4 one-dimensional representations in this case for the dihedral group of what I hate. Note the count here that 1 squared plus 1 squared plus 1 squared plus 1 squared plus 2 squared is 8. So this is really everything. So the 2-dimensional times itself is the sum over all the 1-dimensional ones. And whenever you tensor a 1-dimensional with a 2-dimensional, you get the 2-dimensional. That's why my matrix looks like this. And you do the same game. The leading eigenvalue is 2, which is our dimension. The second largest eigenvalue is 0. We'll come back to that in a second. You write down, let me get rid of the matrix. The matrix is now in the way. You write down the corresponding eigenvalues. Sorry, eigenvectors. Turns out that there's a leading eigenvector and there's another leading eigenvector. So the higher multiplicity here, there are 2 eigenvectors. You just write them down, do the same game, and you get this alternating behavior. Let me go back to the formula. Depending on how often the leading eigenvalue appears around the unit circle, could be 2, -2, could be any root of unity, you get kind of this alternating behavior. Okay, so and what the Bn does is it goes up, and so it has an even odd pattern. You can kind of see it here. Whenever, I mean, it should grow like the leading eigenvalue, but there's another eigenvalue of the same absolute value. So they either go against one another, or they go with one another, and this is exactly the pattern you see here. You go either against one another or with one another, depending on the parity. And you just write down the formula, you just solve it. I just did it for you. I don't expect you to kind of do this in your head right now. It's an eigenvalue problem. You just solve it. And you get this formula of the growth rate yn. And note that the second largest eigenvalue is 0. So the overall growth rate should be 2 over 0 to the n, which is very, very boring, which is 0 to the n. And it turns out that this formula is actually then spot on. So the formula is spot on if and only if the second largest eigenvalue is 0. Now, second largest eigenvalue controls kind of the variance in this problem. I hope that makes some sense. Okay, let me say it again. So really just reduce everything to an eigenvalue and eigenvector problem that you just solve for the matrix, and you get the largest eigenvector, the leading eigenvector is the dominating growth rate, and you get the correction term from the eigenvectors. So that's all that's going on here. And I did several more examples. For example, you can just solve the whole problem now. For a group, for a finite group, you can just solve it, and you get a closed formula for asymptotic property, which you don't need to remember that one. Doesn't matter how it looks like. The point is it's a closed formula, and you can formulate it completely in terms of character theory. Something like certain values of characters in the character table. You just solve the problem, the eigenvector problem, and you get a closed form. For any representation of any finite group in characters. But what I just showed you is way more general. Don't need to remember that formula. Okay. And you can just solve that for anything you want. I just did a few examples. You can solve it for the symmetric group, for example. Kind of a fun fact that appears here for a symmetric group. If you do it, so there's of course our leading growth, which is a dimension, and then you have a term, whatever it is, but the term itself is independent of the representation. It only depends on the symmetric group. Yeah, so some factor that's always the same for any representation you take. The same happens for any finite dimension, for any finite group. So you have the overall growth rate, the dimension, and then a term that only depends on the group and not on the representation itself. That's an interesting fact. And I just solved it for some other case. You can solve it. I mean, it's a character problem. You just open your favorite character table and you can solve the problem. I hope that makes some sense. Yeah. But you can really do a lot of things. You can do categorical things, and I just did it. I will skip the calculation. But you can get nice formulas here. You can get if you do categories, it's an eigenvalue of something. So an eigenvalue doesn't need to be an integer. And here's an example where you don't get an integer. You don't need to get an integer, but the same principle still works. You can just solve it. Whatever. I did a few more examples. That's how the formulas look like, right? Overall growth rate, some correction term. And this is a really wonderful problem to give to a student, to just give them a group, give them a representation, and let them do the calculation. So here's another example. Finite group SL2, characteristic P. There you go. That's a formula that works. And you can see here the convergence rate is really slow. Because in this case, I didn't list it, but in this case, the leading eigenvalue is 2. And the second largest eigenvalue here in characteristic 5, for example, is the golden ratio, which is 1.6 something. Golden ratio, what is it? 1.61. Did it? So difference is fairly small and it will take a while, but it still kind of goes exponentially fast. The difference goes exponentially fast. So wonderful problem for a student.
Can I ask one question?
Yeah, go ahead.
SL2 if P, it is a finite group. I forgot the order of that. What was the order? Number of elements in SL2 if P?
That's a good question. I always forget that one as well.
No, the reason why I'm asking is the following. You said in the beginning that the categories that we consider satisfy Krull-Schmidt property. So it means more or less like our representations should decompose into simple factors, right?
No, it's more like the decomposition is unique. That's Krull-Schmidt.
So I see. So I am wondering if your theory works for modular representation theory. I mean, where the
Absolutely.
order. Excuse me? Yeah.
Yeah, absolutely.
Oh, I see. So okay, then no problem.
Yeah. So the theory totally works. I'm just choosing the examples to be a little bit easier.
Okay.
Any other questions? More examples. I have a lot of examples. Note that the overall growth rate is always given by an eigenvalue of a matrix. So it's always kind of eigenvalue to the end. So it's always exponential in all of these cases. Very general setup, not necessarily finite groups. Anything essentially. All right. Let me just briefly tell you about. Oh, I actually had the example. So the variance is bounded. The variance is always bounded by the second largest eigenvalue to the n. In my SL2 example from before, there was a golden ratio 1.68, and yeah, it's pretty much spot on bounded by 1.618 to the n. So largest eigenvalue, overall growth rate, second largest eigenvalue, variance, eigenvectors, the asymptotic formula. Completely reformulated the whole problem from the beginning, which looked very difficult. You can completely formulate it in terms of linear algebra. So you really just need to calculate a few eigenvalues and a few eigenvectors. I hope that's a reasonably nice answer so far. The only problem that you should observe here is that it is really like a game of finite matrices. So this really only works if I have finitely many objects, finitely many decomposable objects in my category. So what can you do actually in general? Kind of the question I would like to address in the final 10 minutes. And it turns out that you can do something, but you eventually will kind of leave the nice world of linear algebra, and you eventually will see the first instances of what people would study in dynamical systems and feels like this. So as soon as you hit this boundary of maybe we're not studying a finite group anymore, but maybe we're studying an infinite group, it gets more interesting in some sense. It's a bit more difficult than an eigenvector problem. But for finite groups, or everything finite, essentially, finite categories, it's always just an eigenvalue problem.
So we have to study spectral theory probably.
Lise zamanı bir yarışmaya katılacaktım. Bir gitariste ihtiyaç vardı. Ben gitar çalıyorum dedim ve dahil oldum ama ben gitar falan çalmıyorum asla.
I think someone is unmuted.
Gitar çalmak ne kadar zor olabilir ki? Yani çok zor olmasa gerek. Bu yalanda kendime bir hafta verdim ve okula bir hafta kolumu sargı beziyle sararak gittim mesela. Çünkü benden gitar çalmamı isterler.
Okay. Sorry, you had a question with spectral theorem?
I was just saying that maybe one has to use spectral theory because we may have linear operators on infinite dimensional vector spaces.
Yeah, that's a good idea. That's actually a good idea. That's roughly what I'm going to show you in the last 10 minutes. That's exactly right. Yeah. That's a good intuition. But let me just do it. So what I know about it, it's got a lot of work in progress. Oh yeah, let me just skip that. So it turns out that the correct notion that you could study here is a random walk. So instead of thinking about my little matrix here, I already had that. Where's my little matrix? Okay. Let me get rid of this. Instead of thinking about a matrix, I could think about a graph. So every matrix corresponds to a graph by just writing down as many vertices as you have rows and columns, and just connect them according to what you see in the matrix, right? Vertex 1, 2, 3. Vertex 1 is connected to 2, so you draw an edge. Vertex 2 is connected to 1 itself, so you draw this edge in 3, and 3 is connected to 1. Every matrix corresponds to a graph. Let me just think about graphs now. Let me go back to where I was. This one. Yeah, I think about a graph. Okay, right now, just any graph. We'll zoom into my problem in a second. And I would like to, what I really need to do to make this operator approach that you just mentioned work in this case, I need some certain type of graph. I will come back to that in a second. And I really just take a random walk on that graph, the simple random walk where you just, every edge is chosen with the same probability. So just do that on my little graph, like on the integers, for example, I can take a random walk on the integers. That's a coin flipping experiment. Heads gets you right, tails get you left. That's what I'm going to do. And the question is, how often do we visit a vertex? And there are two notions people study in this dynamical system operator algebra type thing is a recurrent and transient, and they are opposite of one another. Recurrent is the one I have here on the slide. We hit every vertex, we do a random walk, infinitely often with probability 1. This is this idea of you will find home, right? You will eventually come back to the origin. If you think about a coin flip experiment, eventually you can have a long run of heads, but eventually you will have some tails and you will hit the origin again. So this is a recurrent problem. Every finite graph problem is recurrent. A little bit boring because you only find many options. So eventually you will hit everything infinitely many with probability 1. That's called recurrent. The opposite of recurrent is transient. Transient is kind of you walk away from the origin eventually. Okay. It turns out that this is what you need in order to make the operator thing, the operator idea with spectral theory work. So you need to study graphs and you need to divide them into two classes, whether they're recurrent or whether the random walk is recurrent on them or whether the random walk on them is transient. So random walk on the Z here, for example, is recurrent. That's really just a coin flip experiment. Random walk on any finite graph is recurrent as well, just though you don't have enough options. So eventually you will hit every vertex infinitely often. And there's a really nice theorem which is due to Polya. Polya studied this problem for the first time about almost 100, or not almost, more than 100 years ago from now. And this the easiest type of graph. So if you know that all finite graphs are recurrent, the easiest type of infinite graphs that come to mind are the standard lattices Z to the D. And you can easily just classify them, whether they're recurrent or transient. So here's a random walk in 3D. So Z to the D is a recurrent problem if and only if D is 1 or 2, and otherwise it's transient. So this is kind of this drunkard will find their way home, but the drunken bird might get lost type of thing. So if you do a random walk in 3D, you're not guaranteed to come back to where you started. If you do a random walk in 2D, with probability 1, you will come back to where you started. Transient is exactly the opposite of recurrent. So Polya gives this classification of random walks on these easy lattices, whether they are transient or recurrent. It's a really beautiful theorem. So dimension 3 it breaks apart, it will be transient from dimension 3 onwards. And it really boils down to an analysis what the binomials do, because if you just think about the number of paths in one of those lattices, they grow like a binomial around the lattice. And Polya essentially studied the binomials, the growth of the binomials on those lattices. It turns out in this 3-dimensional case, something changes. Ooh. Okay, and kind of the fun is that you want to apply this strategy of writing down generalized eigenvalues, generalized eigenvectors on potentially infinite categories. And it turns out that you can do that if and only if the setting is recurrent. So if and only if there's some finiteness built in the random walk you take. If it's transient, the spectral theorem won't apply anymore, and you kind of really need different methods to do it. I'm not quite sure what will work. But if it's recurrent, you essentially apply the same strategy, now with a potentially infinite matrix, and you just talk about a spectrum instead of an eigenvalue, and you just talk about a generalized eigenvector instead of an eigenvector, but you can still run the same setting. And this is essentially an if and only if. Okay, let me just say that again. So recurrent growth problems, for example, any finite tensor category. So as soon as you have finitely many simple objects, it's a recurrent problem. Representations of a group, an arbitrary characteristic is a recurrent problem. You can always apply the strategy. In a recurrent setting, you can always apply the same strategy, and in a transient setting, I don't quite know what to do. So if you know that, you might want to, and that's where I will end, you might want to classify the settings where you have a recurrent problem, because then same strategy as before applies, just with an infinite matrix. And otherwise, you really need to come up with different strategies. You will see very strange fractal behavior and very difficult problems will arise. So we kind of know how to do it in special cases, but in general, we don't. So you want to somehow classify the situations where your problem has a solution using spectral theory, has a solution using using the eigenvalue approach. And we can. It's kind of a nice theorem, kind of a nice analog of here what was Polya again. Polya says this one. So the random walk on the lattice is recurrent if and only if D is not too big. And the analog is the following, which is really just a reformulation of Polya. So I still contributed to Polya. So you take a group and take a faithful representation. You could drop the assumptions, but essentially the random walk on the representation category of the group is recurrent if and only if your group is finite, or it is an extension, well, virtually one of Polya's groups. So it's an extension by a small z or z squared. So it's essentially never recurrent, right? Only finite groups and a little bit more if you're a recurrent problem. And exactly in those cases is where the spectral theory applies. Okay. So again, kind of the analog of Polya's representation in this setting is essentially the same. Finite groups are recurrent, representations of finite groups are recurrent, and not much more, just exactly the two cases of Polya, z and z to the d. And in all other cases, I don't know an answer yet, and you need to come up with a case-by-case analysis to analyze questions 1, 2, 3. I'm not saying we can't do it. Let me just finish here. I'm not saying we can't do it, but I don't know a general strategy, right? So in the recurrent case, I know a general strategy, but essentially nothing is sadly recurrent. And in all other cases, we'll see. Thank you so much for listening.
Danny, thank you very much for this very interesting talk. Any questions or comments?
Please.
So, for example, if we consider compact groups, I mean, the representation theory of compact groups is quite close to representation theory of finite groups. So maybe can one extend your theory to that setting?
That is possible, but we haven't thought about it. Yeah, exactly. So you're absolutely right that looks very similar to representation of finite groups, but we just haven't thought about it yet.
So you were thinking about these categories, but you switched to thinking about categories of representations of affine semi-group superschemes. And I was just wondering what kind of categories those representation categories are.
Oh,
are there some adjectives?
Yes, the key feature they have is they are symmetric. That's something you definitely need. And they have a fiber functor to vector spaces. These are the two adjectives you need. And then you can just replace, you just use any category to satisfy those two features.
Great, thank you.
So what you are saying is that via Tanaka duality then, those are given, their category is equivalent to representation category of certain what you call super schemes, right?
Yeah, exactly.
So there we drop the monoidalness, right? Or it is still monoidal, the category?
No, it's still monoidal. It's even symmetric.
Just symmetric category with a fiber functor.
Yeah, symmetric is a special monoidal plus symmetric.
I see. Okay.
We don't want monoidal.
Any more questions or comments?
Yeah, just is the fiber functor itself a monoidal functor?
And fiber functor by definition is a symmetrical monoidal functor.
Okay, thanks.
We say strong monoidal. It preserves the tensor product.
Exactly, yes.
Yes, yeah. And the symmetry.
Exactly, yeah.
So not lax or oblong.
No.
No.
Okay, thanks.
If there is no more questions or comments, let's thank Danny once more. It was really very interesting talk. I mean, it combined many things all together. Very inspiring talk. Thank you, Danny. So we will meet 2 weeks later. Our speaker will be Michael Schulman from University of California, San Diego. But I mean, the timing will be this time just the opposite. We will meet at some time like 8 o'clock in the evening. So in Australia, probably it will be very early in the morning then.
Probably will be nighttime or something. Yeah, exactly. Yeah.
But we have our YouTube channel now, and we started putting all the recordings so you can watch from there. So
Yes.
to see all of you 2 weeks later. Bye-bye.
Thank you so much. Bye-bye.
Oh, we thank you very much.
Bye-bye.
Bye.